Here we are in Unit 6. Unit 6 is going to tie together slope fields, differential equations, exponential growth, Euler's method. We're going to learn some new strategies for integration by parts, using partial fractions, and just really analyze how do we approach an integration problem from start to finish. Then we're going to talk about logistic growth, and last but not least, we're going to end Unit 6 with L'Hopital's rule. So 6.1 is going to focus on differential equations and solving differential equations. So a differential equation is any equation containing a derivative. There are many different types of differential equations. Some of you will probably go on and in college take differential equations classes where you learn a ton of different methods to solve. However, in this class, we are only going to solve differential equations in which we have separable variables, meaning we can get all of our x's on one side and all of our y's on the other side. To do this, we're then going to be integrating both sides of the differential equation in order to solve. When we do this, we're going to come up with a general solution, meaning a solution that still has a constant of integration. It still has a plus c. And if we are given an initial condition, we can then solve for a particular solution and no longer have a plus c value. So I'm going to show you how to do this and tie together these steps 1 through 5 on solving differential equations kind of at the same time. And then we're going to do a decent amount of practice on each following through these steps. So the very first step down here says write using dy dx instead of y prime. So x plus 2y dy dx equals 0. And then we're going to separate our variables. We want all of our x's to be on one side. So 2y dy dx equals negative x. Let's go over here and try and write so that you can actually read this. And then this is going to feel a little weird because dy dx is not technically a fraction, but calculus allows us to treat it like a fraction. So what I'm actually going to do is I'm going to multiply both sides by dx so that I have my dx's and my x's on the right and my dy's and my y's on the left. And I know that seems like something we shouldn't be allowed to do, but we are allowed to do it. Now that we are here, we can integrate both sides of this equation with respect to y on the left side and respect to x on the right side. So the integral of 2y dy is going to be y squared. The integral of x dx is going to be x squared over 2. And since c just represents some arbitrary constant, we can just put plus c on either of the two sides. We don't need to put it on both sides. And then let's go ahead and isolate y, which you're going to do anytime that that's possible or logical to do that. So we're actually going to get two separate equations. We're going to get that y equals the square root of x squared over 2 plus c. And we're going to get that y equals the negative principal root of x squared, or the negative root of x squared over 2 plus c. So these are our two equations that represent the solution, the general solution for this differential equation. So first, make sure you have dy dx instead of y prime. Then separate, get all the y stuff on one side, including dy, and all the x stuff on the other side, including dx. Then you're going to integrate. You only need one constant. However, if you are manipulating both sides of the equation, you may need to use subscripts. You may need C1 and then C2 and then C3. If you're doing some basic math to solve for y, you're going to need to change those constants, and I'll show you what I mean in this next example. Then if you are given an initial condition, you can actually find the particular solution. So when we still have a plus c, that's our general solution, and when we can solve for that c value, that is our particular solution. So let's look at A, example A down here. So first thing I want to do is I want all my y's on both sides, so I'm going to multiply both sides by y. And I'm going to multiply both sides by x. So I get all of my x's on the right and all of my y's on the left. Then I'm going to integrate. The integral of y dy is going to be y squared over 2. The integral of x e to the x squared. So I'm going to reverse the chain rule here. If you need to use U substitution, pause the video to do this. But if as long as I have a 2x here and a 1/2 in front, that's going to reverse the chain rule. So I'm going to be left with 1/2 e to the x squared plus c1. Now I need to solve for y. So I need to multiply everything by 2. So instead of just changing my c1 to be 2c1, I'm just going to rewrite it as something else. I'm just going to rewrite it as c2. So I multiplied everything on both sides by 2. And now I'm just, instead of writing 2 times c1, which you could do, but that seems sort of silly. C just represents any arbitrary constant. I'm just going to change it to be c2. And then I'm going to write this as two separate equations. Y equals e to the x squared plus c2, and y equals negative square root of e to the x squared plus c2. So these are our general solutions for part A. Part B is giving us an initial condition and asking us to find the particular solution. So notice here that y is negative. That means we're going to use this equation with the negative square root. So we're going to say negative 3 equals the square root of, the negative square root of, e to the 0 plus c2, and we're going to solve for c2. So I'm going to square both sides. c2 is going to be 8. So the particular solution, the exact solution with this initial condition, is going to be y equals negative the square root of e to the x squared plus 8. Okay, let's do some more practice. Number 1 here, I am going to first separate my variables. So I am going to multiply both sides by dx, and that will give me dx times y minus 2 equals x dy. But I need my x's and y's to be together, so I'm going to divide both sides by x and divide both sides by y minus 2. That's going to give me dx over x equals dy over y minus 2. Then I'm going to integrate both sides. This is going to give me the natural log of the absolute value of x plus c equals the natural log of the absolute value of y minus 2. So this is kind of ugly looking. I want to actually solve for y here, so I'm going to raise this entire equation e to the power of all of it. So that's going to give me e to the natural log of the absolute value of x times e to the c. So I'm going to split this up, equals e to the natural log of the absolute value of y minus 2. And over here, what I'm going to do is, well, e to the natural log of absolute value of x is just going to be the absolute value of x. And e to the power of c to the first, I'm just going to change that. And I'm going to call this constant number 2, because this is a constant. That's exactly what it's doing, or it's a scalar in this case. So I'm going to just change it, and now it's going to be called c2. Over here, I'm going to get the absolute value of y minus 2. Now, I want to get rid of this absolute value. So what I'm going to do is I'm just going to say plus or minus x, right? Whether x is positive or negative, that times c2 equals y minus 2. So I'm going to just drop the absolute value on both sides, and I'm going to drop it by just putting a plus or minus on one of the sides. That will encompass whether it was positive or negative. And again, I want to make this as simple as possible. So I'm going to take this plus minus and this c2, and I'm going to take that together and call that c3. So x times c3 equals y minus 2. So y is going to equal x times c3 plus 2. There is my general solution. So you may need to pause the video and go back, because we just did a whole lot of weird math when we were changing our c values there. So feel free, pause and go back and watch that part again. And then the last thing we need to do here is we need to find the particular solution. So we're going to plug in what we know. 1/2 equals 1 times c3 plus 2. So c3 is going to be negative 3 over 2. So our particular solution is y equals negative 3 over 2x plus 2. So we have now done about 3 of these problems together. So what I'm going to do is I'm going to encourage you to pause the video and work through numbers 2 through 4. And then you can unpause the video and check how you did. But I'm not going to walk through them each step by step. I'm just going to put the solutions in there for you. So notice on numbers 2 and 4, it does not ask you to isolate y. There's just too much going on there, and it's not worth it for us to do that. It doesn't say that on 1 and 3, which is why you do need to isolate y on both numbers 1 and 3. So the particular solution on number 2 is 2/3 y to the third plus 3y equals x to the third over 3 minus x plus 3. On number 3, our general solution is going to be y equals the square root of negative 2x squared plus c2, and y equals negative the square root of negative 2x squared plus c2. Since for our particular solution we need y to be negative, we're going to use the second equation here and solve for c2. We're going to get that c2 is 24, and you can see our particular solution there. I specifically told you don't need to isolate y on number 3, so you're going to get 1/3 natural log of the absolute value of 3x plus c equals negative natural log of the absolute value of y. And then you can substitute in the 0.1e to find your particular solution. And I am totally out of space, so this is going to be my c value, and that would get substituted in back here. So you'd have a very messy looking equation here. All right, pause the video if you need to keep checking those answers. We're going to move on to exponential growth. Now we're going to focus on exponential growth. So when the rate of change of a population or a substance is proportional to the current amount of whatever that is we're talking about, we can model that using exponential growth or decay. And we have done this as far back as Algebra 2. But now we're going to tie some calculus into this. So suppose that the rate of change of whatever we're talking about, population, substance, suppose that that rate of change with respect to time, meaning that y is a function of time, is proportional to y itself. We can then represent it as dy dt equals ky, where dy dt is that rate of change, k is a constant of proportionality, and y is the amount of that substance at any particular time. So using what we just did, let's use the separation of variables to actually solve this differential equation. Now remember that k is a constant, so I can just stick dt with k, and that's not a big deal. So I'm going to divide both sides by y, so dy over y equals k dt. Then integrate both sides. So that's going to give me the natural log of the absolute value of y equals k times t plus some constant. Well, now I am going to solve for y here, which means I need to take everything e to the power of both sides here. That's going to give me the absolute value of y. E to the natural log of the absolute value of y is just the absolute value of y, equals e to the power of kt plus c1. Now remember that if I have e to the power of kt plus c1, that's the same thing as e to the kt times e to the c1. That's just basic Algebra 1 rules of exponents. So this is really just some new constant. So I'm going to represent that now as c2. I'm just going to call that my c2. And I could drop this absolute value for y. That's just going to be the changing a scalar. So what I can actually say is y equals, I'm going to make it c3 now to manage with this. How do I get rid of absolute value? I can just drop it and change this to be a new scalar, right? If it was negative, that's going to be sucked up in the c3. If it was positive, same thing. So c3 times e to the kt. So there's our solution, our general solution to this differential equation. And you will see it generalized down here. This equation is called the basic law of exponential growth or decay. You may have seen something really similar back in Algebra 2 where you saw a equals or y equals pe to the rt. Same concept, same derivation, and that's why we couldn't prove to you where this formula comes from in Algebra 2, because you need some calculus, you need some differential equations to be able to prove that formula. So this equation is going to be used on many occasions, typically when the problem tells you that we have this constant of proportionality or that you are using the basic law of exponential growth or decay. So remember that the initial value is constant, as is the constant of proportionality. So C and K are not things that are changing with respect to time. What's changing with respect to time is Y, and obviously time is changing as well. So those are our variables that could be changing. So now we're just going to work through a couple example problems, and then we're going to wrap up these notes. What is the rate of growth of the population of a city, in a city whose population triples every 100 years? So we're looking at triples every 100 years. Assume that the growth can be modeled. So notice it's telling us that we are allowed to use this formula. Express your answer as a percent. So we are using this. We are being asked for what is the rate. So we want to find K. Our goal is to figure out what K is. So let's plug in what we know. We know that 3 times the initial population is equal to that initial population times e to the 100K, because it says 100 years. Not sure that anyone was alive long enough to be around for this whole tripling effect. I'm going to divide both sides by c, so I'm going to get 3 equals e to the 100K. How do I get my variable out of the exponent? I natural log both sides. The natural log of e to the 100K is just going to be 100K. And then if I solve for K here, if I take the natural log of 3 and I divide it by 100, we're going to get that K is equal to 0.011. And the question asks us to represent this as a percentage, so 1.1%. Why don't you go ahead and pause the video and see if you can work through number 6 on your own. Suppose there are 200 bacteria. 2 days later, there are 300 bacteria. Assuming the rate of growth is proportional to the number of bacteria present, and they're telling us to use this formula, how many bacteria will be present 5 days after the start? So we want to know when t equals 5, we want to know how many bacteria, which is going to be our y. So y equals c e to the k t. No, you don't have to write that every time, but it's good until you have it memorized. So 300 equals 200 e to the 2k. So after 2 days, this is where our numbers are. So this is going to be 3 over 2 equals e to the 2k. I'm going to natural log both sides. And then divide that by 2. So k equals natural log of 1.5 divided by 2, which is going to give us 0.2027. And I would actually just keep that number in your calculator and reuse that number so that you're not rounding too early. So 3 days later, we're looking at y equals 200 times e to the amount that we just found, 2.2027, except I would prefer that you don't round, and we're going to multiply that number by 5, and that's going to give us 551 bacteria. All right, last question. Newton's law of cooling states that the rate of change of the temperature of an object is directly proportional to the difference of the current temperature of the object and the ambient temperature. A hot pocket is removed from the microwave with a core temperature of 398 degrees Fahrenheit. So before I even keep going, I'm going to write that as an ordered pair. At time 0, we're at 398 degrees. And we're in a room that is a constant temperature of 68 degrees Fahrenheit. After 5 minutes, here's our second ordered pair, you take a bite and burn your mouth because the hot pocket is still at 242 degrees Fahrenheit. How long, so we're looking for time, how long will it take for the hot pocket to be ready to eat? And they're telling us that that temperature where it's ready to eat is 155 degrees Fahrenheit. So we're sort of going to set up a system of equations here. The very first thing that we're going to do is use our first one, and we can actually use this first one to solve for C. So we can say 398 equals C times E to the K t, but in this case t is 0, which means right away, oops, don't forget, plus our room temperature, which was 68 degrees. So right away we can solve for C and get that C is 330 degrees Fahrenheit. Now I'm going to use my second ordered pair here to figure out what K is. So I first figured out what C is, now I need to figure out what K is so that I can plug everything in to solve for T. So 242 equals that C value we just found times e to the K, and what is T here? T is 5. So I'm going to do like 3 things at once because I'm running out of space here. I'm going to divide, oops, why do I keep forgetting room temperature? I'm going to subtract 68, that's going to give me 155. I'm going to divide both sides by 330, so I'm going to get 155 over 330 equals e to the 5K. Then I'm going to natural log both sides and divide by 5. So natural log of 155 over 330, let's just say 1/5 times that, equals K. And obviously that's a calculator problem here. You're going to get that K is negative 0.151. And then last but not least, our ultimate goal on this problem, we were doing all of this work so that we could figure out how long it is going to take us to eat our Hot Pocket. But let's be real, we probably could have already eaten our Hot Pocket by now in this situation. So how long is it going to take? We're looking for the temperature to be 155 degrees Fahrenheit. Our C value is 330. E to the K value we just found, negative 0.151. T is what we're looking for. I'm not going to forget my plus 68 this time. So I'm going to subtract 68 and divide by 330. 87 over 330 equals e to the negative 0.151 t. I'm going to natural log both sides. And then I'm going to divide by negative 0.151, which is going to give me that t equals 8.821 minutes. Man, that's a long wait. I'm getting hungry just thinking about these Hot Pockets. Okay, so recapping what we learned in this lesson, we first talked about solving differential equations. And we do that at this level of calculus only by separating our variables. So getting all of our x's on one side and our dx on the same side and all of our y's on the other side so that we can then integrate with respect to the variables on each side. Remember that when you have your plus c and you're manipulating the equation, every time you multiply or subtract or add, you need to change the subscript on your c. When you need to find a particular solution, you're going to plug in the ordered pair they give you to find C and then rewrite it. And then we lastly talked about exponential growth and really proved something that you used in Algebra 2, having no idea where it came from. Remember that when you're doing problems like these, they have to tell you either that you're using the basic law of exponential growth or specifically like they did in number 6, tell you to use this formula. That's how you know that this is the type of exponential growth that you are looking at. Looking forward to supporting you on this in class. Thanks for listening.